Okay, so to continue from yesterday, let's just kind of add a little bit of guidance in this proof. So we started this one yesterday. We said somebody has made a conjecture that when you add up all of the positive odd integers, the formula can be used to do that is just take whatever the number is of the term and square it. All right, that's our conjecture. So this is going to be what you will be given. Let me write in here just to kind of add to what we said yesterday. This would be your given statement. So that's what you're going to have to have given to you in order to start. Okay, then step one is what we did here. Right? We showed that when n equals 1, the statement is true. That was step one. Step two. Now this is where, I might lose you for a minute, and I'll be honest with you, when I first was teaching this for the first time, I had a little bit of problems with this step two, but I'll explain as we go through this why it works. So step two is assume I guess I'm writing P sub k. P sub k is true. And that's what we did here. Okay, step two was assume that P sub k is true. Yesterday we just said write this out because that was our goal, to be able to write it. And then step three is the actual proof. So step three, show P sub k plus 1 is true. Now, that is where the magic is going to happen. And when we finish this proof, I'm going to go back and revisit step two because I want to talk a little bit about it. Okay. I'm going to keep these two at the top of the page because I'm going to use them as we move through this process. So I want to show that P sub k plus 1 is true. In other words, I want to show that all of this, when I add it together, can be written as just k plus 1 squared. I want to show that those two things are equivalent. The problem I have is this dot, dot, dot right there. I don't know what is in that dot, dot, dot. Okay, so I have a little bit of an issue with that. I can't simplify the left side a whole lot until I can find a way to get rid of the dot, dot, dot. And we'll come back to that in just a minute. Let's do as much as we can. All right, so I'm going to start out by just simplifying the left side as much as I can. So I start that out by just writing what I have, 1 plus 3 plus 5 plus 7 plus dot, dot, dot. Now let me simplify what's in parentheses there. So that 2 times k plus 1 minus 1. What is k plus 1 minus 1? Let's simplify what's inside the inner set of parentheses there. Okay, so I just have 2k and then minus 1. Okay, so that first set of parentheses all simplifies to just be 2k minus 1. In the second set of parentheses, distribute my 2. I'm going to have 2k. So I'm not going to write this all out, but I would have 2k plus 2, but then subtract 1 is going to give me plus 1. If you have any trouble with that, do it in 2 steps. All right, it's okay to do it in 2 steps. I'm just trying to, do some of the simple algebra in our head if we can. Now here's where it's the magic of this proof happens in the next step. Again, remember, I'm trying to show that the left side and the right side are the same. Look up at what we assumed to be true up above. Okay, what we assumed to be true up above was that 1 plus 3 plus 5 plus 7 plus dot, 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 all the way up to 2k minus 1 can just be written as k squared. We assumed that that was true. So I can use that in other parts of my proof if I need to make a substitution. So look at what I've written. I have 1 plus 3 plus 5 plus 7 plus dot, 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 up to 2k minus 1. I know some of you are maybe having trouble with the fact that this is here, but that's what we would have right here, right in front of the 2k minus 1. Okay, that would be the term before it. We talked a little bit about that yesterday. But this entire expression is the same as this entire expression. So if I'm assuming that this is going to be the same as k squared, then I can replace this with k squared. And that's what I'm going to do. That is the most important step, I think, in this entire process. This entire thing can just be written as k squared. Now I've got a little bit more here. I've got 2k plus 1 still. Notice I took the parentheses off of that. I'm adding it. I'm not multiplying it. There's no squared. The parentheses are no longer necessary. So that left side, I've been able to rewrite as k squared plus 2k plus 1. That's awesome. It's pretty much simplified as much as I can get it. Now what I have to do is show that when I simplify the right side, I get the same thing. So that means I'm going to have to do a little bit of algebra here. I'm going to have to think about multiplying out k plus 1 squared. Remember, when we square something, it means you're multiplying that thing times itself. So what we're really doing is k plus 1 times itself. So let's use our FOIL method. First terms multiplied together will be k squared. Outside terms multiplied together would be k. Inside terms would also be k. And our last terms are 1. So just by multiplying out k plus 1 squared, I get k squared plus k plus 1. If I simplify that, I get k squared plus 2k plus 1. And look at what we had on the left side. K squared plus 2k plus 1. We have the same thing on both sides. So what I've just shown is that if we assume it works for some number k, it's going to work for the next number as well. The way we compute k and the way we compute k plus 1 gave us the same equivalent expression in the end. So the assumption that it works for k, I want to just address that for a second. Because as I said, this is the part where I always said, how can I just assume that it's going to work for some number k? Like, why can I make this assumption? And the reason that I can make that assumption is because k could be 1. Okay? I just showed that it's true for 1. This formula works when n equals 1. So let's just say that, all right, what if we're saying that the k is 1? All right, so I'm assuming it works for 1. I just showed it worked for 1. I'm using the fact that I know it works for 1 to show that it's going to work for the next term, for term 2. Well, now I know that 2 is true, so it's going to work for the next term, which is 3. And I can continue that logic for an infinite amount of time. The key to this is you have to show that it works for that first term. And then from there, it's just a domino effect. So I've shown that this works. I'm going to finish this up. There's a lot of different ways you can finish up a proof. We talked a little bit about this when we did trig proofs. I like to put a little square at the end of my proof to say, yep, we're done. It works. I've finished. It's like the period, exclamation point, whatever, at the end of a proof. These are really similar to trig proofs as well. Because I want you to notice that when we were doing this simplification in this whole section here, at no point did I add or subtract the same thing from both sides. At no point did I multiply both sides by something, right? We aren't able to treat it like an equation because I don't actually know if it's true until I show it's true. So we just work on one side and try to make one side look like the other side. And we did that with our trig proofs as well. Okay. Let's do just one together today. So that was finishing up the one we started yesterday. Let's do one from start to finish. A little more complicated, but we're going to go through the entire process all at once. So I think this would be example 3, if I remember right. So show that S sub n is true for all n using induction. All right, so what's S sub n this time? S sub n is going to be 1 squared plus 2 squared plus 3 squared plus all the way up to, now leave a little space here because that's how it will be written without the little extra plus sign here. I'm going to come back to that in just a second, but just leave a gap between 3 and n squared. What I'm conjecturing, or what somebody conjectured, is that if I want to know this sum for any n value, you can find it by doing this equation or this formula. And if you have not started on a new page, I would encourage you to do so, because this is definitely going to run onto a second page. Or at least start on a page where you can see it all at once. Okay, so this is how it would be given to you. What I want to do is sort of add something in because it's going to help us down the road. The way this is written, it's written so that it starts at 1 and it goes up to n. But I want to look at what's right before the nth term. So if we're looking at the sum of 10 terms, the term right before that is going to be the 9th term, or the 10 minus 1 term. So I want to put in here n minus 1. So whatever n is, just go backwards 1, make it n minus 1. Again, it looks like we maybe made it more complicated, but I think in the long run it's going to make things a little bit better for us. All right, so that's what we're given. All right, this is somebody's idea. They're saying this works. It's our job to prove it. So we have 3 steps. The first step is to show that it works for n equals 1. We have to have it working for the first term. I think you would agree. The one we just finished was not, it almost seemed like it was obvious that it worked for n equals 1, because it kind of was. All we had to do was square the n value, and that gave us the sum. This one's a little more complicated. Okay, so to show that it works for the first term, we're saying the first term is 1 squared. So S sub 1 would be 1 squared. If we square 1, that's just 1. So in order for us to go any further with this process, I have to make sure that when I plug 1 into this expression, I get the same thing I got here, which just so happens to be 1 as well. All right, so I'm going to plug in 1 into that big expression. So I'm going to have 1 times 1 plus 1 times 2 times 1 plus 1, all divided by 6. All right, so again, all I'm doing is plugging in 1 for n up here. And then let's simplify that. So I will have, let's see, 1 plus, not 1 plus, 1 times 1 plus 1, which is 2, times 2 times 1, 2, plus 1 is 3, all over 6. Then I've got 6 over 6, which is 1. So what I've done is I've shown that it works for that n equals 1 term, because I get the same thing whether I use the formula or I generate the terms in the sequence. Okay, so that's the very first step that we have to take. We've got to have a baseline. This is our baseline. Show it works for the first term. Okay, step 2. Let's assume it works for some k value. So some random k value. Doesn't have to be random, it could be 1, okay? And we just showed it worked for 1, so our assumption is safe there. Okay, so assume it works for some k value. So let me write that out. So S sub k will be what we get when we replace all of the n's with k. So I'm just going up in that expression I wrote up above and replacing every n value with k. And I do it on both sides of the equal sign there. So assume it works for some k value. So far, nothing too crazy. The first 2 steps aren't all that bad. It's that third step is where all the meat is of the proof. All right, so step 3. So we're going to show it works for k plus 1. This is where we have to be careful. There's lots of places we can make mistakes. The biggest kind of advice I can give you is don't rush this process. And also keep in mind, our quiz is a take-home quiz for this topic. So in no way am I expecting you to walk in on any given day and work through proof of this in one class period. Okay, I'm expecting you to be able to use your notes, which hopefully you're taking good notes, talk to each other, work together, and come up with a proof. We'll talk about the difference between working together and cheating when we get to the actual day of the take-home quiz. But for right now, just know that the pressure might be off a little bit. It's going to seem a little crazy here for a minute, but when you get to the point where you're trying to do this on your own, hopefully it should be better. So to show that it works for the k plus 1 term, I've got to write the k plus 1 term. So let's write the k plus 1 term. So this requires us to replace all of our k's with k plus 1. And that starts right here. So this k right here, I'm going to replace with k plus 1. Okay, those underlined things, that's where I made the substitution. Well, now I still have minus 1 squared. I'm going to replace this k with k plus 1. Now, since I was squaring k, I'm going to have to put that in parentheses. So k plus 1 squared. Equals. I have to do the same thing over here. I'm going to use a different color on the right side as we work through this. You'll see why. So that's k. Instead of k, we're going to replace it with k plus 1. Now I'm multiplying, so I'm going to put it in parentheses. Instead of k, I'm going to replace it with k plus 1. Now I still have the plus 1 that came after that. Now we got to be careful here because we're multiplying k by 2 in this situation. So instead of k, I'll write k plus 1, but I have to do so in parentheses. All over 6. So this is just the actual writing of the k plus 1 statement. The rest of what we're going to do is the actual proof that it works, and it's 100% algebra. What I tell my calculus students a lot is that we've noticed this, and they would tell you this as well. The calculus isn't the problem. Calculus is actually pretty easy. It's the algebra that takes your concentration and can be where you make your biggest mistakes. So just take your time. You guys can do this. Your algebra is fine. Just don't try to rush anything. So I want to take a minute and clean it up just a little bit. So I'm going to start by simplifying as much as I can. Let's start with the left side. Okay. So on the left side, let me make sure I have my yellow marker. I've got 1 squared plus 2 squared plus 3 squared plus dot, 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 plus. Okay, let's simplify that expression. What is k plus 1 minus 1? K. So I have k squared. Plus, I'm just going to write this as k plus 1 times k plus 1 for right now. Okay? We'll come back to that. But I want to pause right here. My goal is to try to simplify this left side. I don't know about you, but I have no idea what to do with the dot, 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 right? I mean, that leaves a lot to the imagination. So I'm going to go back up to my assumption up above, which was that it works for some k value. And remember what we did in the last one. We said, look, this 1 squared plus 2 squared plus 3 squared plus all the way up to k squared is showing up right here as well. Those two expressions are the same thing. And we assumed that if we see that expression, we can replace it with this expression, which is really nice. There's no dot, dot, dot here. That's just a regular old algebraic expression. So what I've highlighted in pink, I'm going to replace with that expression. So let's do that. And I'll even use pink to do it. So we'll have k times k plus 1 times 2k plus 1 all over 6. That is the replacement. Now, if we're just looking at what I've written in yellow, there's more. You know, we'll leave it as k plus 1 times k plus 1 for now. Now you notice I'm not writing the green side of the equation right now because or the expression. I don't want to confuse the fact that I can actually do something to both sides. If I was still writing that green side down, I might think, oh, let me go ahead and multiply everything by 6 because it'll get rid of all my fractions. Well, I want to be careful. You can't do something to both sides. It's just like our trig proofs. We've got to focus on one side at a time. So what I want to do here is I would like to be able to add those two things that I have on the left side together. I'd like to be able to add that all together. The only way I can do that is if I have a common denominator. So I'm going to have to multiply this, if I think of this as being over 1, I'm going to have to multiply this by 6 over 6. So I have a common denominator. And now we can start doing the simplification. So I'm going to have one big expression all over 6, right? The whole point of having a common denominator so I can write them as one big expression. I do want to be really careful this first time through, so I'm not going to do too much at once. So let me write this just as k times k plus 1 times 2k plus 1 plus 6 times k plus 1 times k plus 1. Okay, so all I'm doing is I'm writing the sum of the numerators. When you add fractions together, that's how we do it. We get a common denominator, and we write the sum of the numerators. Well, now we've got to do a lot of simplifying, a lot of distributing. There's a lot of just algebra that happens here. So what I'm going to start with is, and I'll highlight the two things I'm going to do first. I'm going to multiply these two things together, and I'm going to multiply these two things together. And I'm doing this just so we're not unclear about what we're actually multiplying in each step. So I've got that k out in front still. We're going to do k times 2k, multiply the first terms, that's 2k squared. Multiply the outside terms, so that's plus k times 1, or k. Multiply the inside terms, that's 2k. And then multiply the last terms, plus 1. All right, second piece of this, I'm just going to multiply k plus 1 times k plus 1. We just did that a minute ago. Okay, so you could go through it and do the FOIL process, or if you remember what we had a minute ago, it's just this. That fraction bar is really awful. Okay, next up. Again, I'm just trying to simplify. I'd like to be able to write this as a single polynomial. So let me simplify this if I can by distributing k and distributing 6. Now, theoretically, you could have simplified that first expression in parentheses if you wanted to. You don't have to, though. Okay, so let's distribute. So I have k times 2k squared is going to be 2k cubed. K times k is k squared. K times 2k is 2k squared. K times 1 is k. And then we'll do the 6. So 6k squared plus 12k plus 6. All over 6. So we've taken it from this really complicated looking algebraic expression. Now we've just got a polynomial, which we can add our like terms together pretty easily. So let's add our like terms together. So we'll start with 2k cubed plus, so we've got, let's see, k squared plus 2k squared plus 6k squared. Is that 9k squared? And then our k terms, so we've got plus k plus 12k, so that's 13k, and then plus 6. That's about as good as I can get it on that left side. So now my focus needs to change from looking at what happened here in the yellow to trying to make the green match it. So I'm going to go all the way back up here to the top. Notice I wasn't writing the other side of that expression at any point because I wanted to save that for later. So now let's turn our attention to what's happening on the right side of that equal sign. So once again, let's do some simplifying. So let's see, we'll have k plus 1 times, so we've got k plus 1 plus 1. K plus 2 times, and then I'm going to sort of cheat a little bit and do 2 steps in one. I'm going to distribute and combine my like terms, but if you need to do this as 2 separate steps, there's nothing wrong with that, okay? So I will have 2 times k, which is 2k. I have 2 times 1, which is 2, but then I need to add 1 to it, so that's 3. All over 6. So I'm doing this in baby steps. I'm trying to do it without doing too many things at once. Okay, now I just have to start multiplying things together. So I'm going to do this in 2 steps like we did in the prior one. I want to take 2 of these binomials and multiply them together first. So let me multiply k plus 1 times k plus 2 first. So do my FOIL process. First terms, I'll have k squared. Outside terms, 2k. Inside terms, 1k, or just k. Last terms, 2. I will multiply that by 2k plus 3 in just a moment. Now, you have options here. You could just start multiplying this out. I don't know. I think it's worth doing one little extra step here and simplifying that first parenthesis a little bit more. So adding your like terms together. So we've got k squared, but then we have 2k plus k, 3k, plus 2. And then we're going to multiply that by 2k plus 3. So, we haven't done a lot of this in this class where we multiply a binomial times a trinomial, but the process is very much like what you do when you're multiplying 2 binomials together. It's just a bunch of distributions. So the way I approach it is I take the 2k and I multiply it by everything in the other expression. And then I'll take the 3 and multiply it by everything in the other expression. So I'm just taking both terms of that binomial and distributing it into the trinomial. So let's see what that ends up being. All right, so let's see. 2k. So let's distribute the 2k. So we have 2k times k squared. That's going to be 2k cubed. And then we have 2k times 3k. That's going to be 6k squared. Then we have 2k times 2. That's 4k. And then we're going to distribute 3. So 3 times k squared, that's 3k squared. 3 times 3k is 9k. And then 3 times 2 is 6. Don't forget, this is all still divided by 6. And then at this point, kind of in the same place we were a moment ago, where we can just start combining like terms. So let's see. I'm trying to keep this lined up with what I had before. All right. So equals. Okay, distribute or combine like terms. So we were going to have 2k cubed. Then I have 6k squared plus 3k squared is 9k squared. And then 4k plus 9k is 13k plus 6, all divided by 6. Now, let's compare that to what we wrote before. And lo and behold, they are the same expression. So I'm just going to write it down here so we have it on the same line. And remember, that's our goal, just like it was with trig proofs, to show that the two sides of the equal sign are the same thing. And we did that. The two sides of the equal sign are the same thing. So I'm just going to add in my little, yep, we're done. We proved it's right. Yay, us. This is a big undertaking, right? This is not something that is completely obvious. And I will tell you this. A lot of people want to know, when would I ever use this? And I will tell you, you probably will never use this specific skill again unless you go into study mathematics. It is very specific to math and the study of math. But the process and being careful with your details and the logic that we're using here, that's what you're sharpening your algebra skills. I want you to just think of it as that. And like I said, in calculus, if you do it, I would say 75% of calculus is just doing algebra. So you've got to have really strong algebra skills. This is one way to incorporate that algebra into our pre-calculus studies. It is a legitimate proof. Like, there are proofs written using this thought process, this induction idea. So it's not something that's just made up for us to study. It actually is useful to do some proofs. For us to try to prove that this statement that we started with originally, for us to try to prove that that statement is true, the S sub n statement, this is the best way to do it, proof by induction. To try to do it any other way will be very difficult. So having this idea is a very useful one for mathematicians. It's also very useful for you to practice your logic, to practice your algebra. Okay, so I know it's a very strange process, and if we look at that proof, that's a pretty, my handwriting always gets bigger as we go. I mean, look at that. It's not for the weak of heart. It's gonna require some focus and concentration and perseverance. You can't give up. I think every one of you can easily do the first two steps, and even setting up the third step. I think you're good there. Just practice the algebra, take your time. Okay?